All right, section 2, we start getting into regression. What we have here in terms of regression lines is we talk about a regression line as a line that's going to model our data. Okay, and so when we get into our regression lines, okay, you could have somebody that thinks this is their regression line. They draw that in thinking that represents or models my data fairly well. Somebody else might think this is a better model. Okay, somebody else might come in with even a third one. Okay, now what we're going to eventually get to is what we call the least squares regression line. Okay, but right now we could draw in any line that we think models that data and use that regression line to make some predictions, because that's what we really want to do with our data, is be able to make some predictions about what's going on. Okay, so when we look at, we're going to talk about our regression equation. Okay, and our regression equation is going to take the form y hat. Okay, that's what we talk about that is y hat. And y hat is our predicted y value. Okay. And it's going to be a plus bx. So thinking back to algebra, okay, again, that's going to be your y-intercept. I already have that over there. Don't need to write it again. Okay, so a is going to be my y-intercept where we cross the y-axis, and b is going to be your slope, your rate of change. Okay, another way to look at that situation, because one of the things we're going to do is interpret that slope as we go along. Now remember, slope again is change in y direction over change in x direction. So how much we go up and down over how much we go left and right. Okay. Now it's different than y equals mx plus b, so you have to make that adjustment as well. Okay. Now we have something that's called extrapolation. So let's say somebody comes in here and gets that as a regression line, and let's say that our x values start at 0. Okay, and maybe they go up by ones. Okay, so we can make predictions now using this equation. What I can do is I can plug in any value I want. So if I plug in x equals 2, what's going to happen is I'm going to take that up. This is going to be my predicted y value, or my y hat. For when x equals 2, that's my predicted y value. Okay, and that's going to be the idea. Now, what extrapolation is if I wanted to make a prediction when x equals 10. Okay, so we're making predictions outside the range of values that we used to get our regression line. And you always have to be careful when we do that. Okay, and you think about in the real world, a couple things they'll talk about is, you know, like unemployment rates, housing, median housing price, and they'll talk about if this trend continues, and that's because they're making a prediction going from, say, maybe the year 2005 to 2014, and now all of a sudden we're going to make a prediction for 2020. Well, that's if these trends continue. So we always want to be careful when we're making predictions outside the range of values for what we use. So here I should only make predictions somewhere between 0 and 5, because that's the x values that I have. All right, now how this least squared regression line idea works is, number one, what we have to find is our centroid. Okay, what our centroid is, it's a point that we find by finding the mean of all my x values and the mean of all my y values. So let's say, for instance, maybe that centroid is here. Okay. And the reason we start with that is anytime we deal with a regression line, it's going to go through that point. Okay, always through this point. Okay, and then what you can do is you can kind of think about what I can do is I could pivot this line. Okay, and maybe as long as I keep it on there, I'm still going to have some form of a regression line. Now, what this least squares idea is when I have a line here, I want to find that distance from the point up to my regression line. Okay, and what they're going to do is they're going to talk about squaring that. Okay, and so we make a bunch of little squares here. That's the actual type of model that we have. So we find the distance we are from that line. Okay, let's try this again. It's not building, and then we square it. And we keep doing that with all these different points. And then what they want to do is come in here, let's say that's this one here, and find the one that has the least area. Okay, you'll never actually have to show that, but it's kind of what's going on. Again, it's all those little squares. Okay, and we find that distance to the line and then square it. Distance to the line and then square it and add up all those areas. And that's what we're looking for, is the least area of these squares. Okay, and that's going to be what we talk about as our best fit line. Okay. All right, well, another thing that's going to be important when we do our regression is what we call residuals, okay, because they become very helpful in a lot of things. And what a residual is, it's the distance between your observed values and your predicted. Okay, so for instance, here is, say, x equals 4. Okay, this is my observed value. My predicted value again would be here. This distance is what's called the residual. Okay. Now, we always want to look at calculating our residuals by taking my observed y, okay, which is going to be y, minus my predicted. And if you remember, predicted again is your y hat values. Okay, so my observed here is smaller than my predicted, so all my residuals down here are going to be negative values. If I looked at this residual, okay, here's my observed this time, here's my predicted. Now my observed is bigger, so all my residuals up here are going to be positive. Now, if I were to add all of my residuals up for my least squared regression line, they'll add to 0. And that's one way we can check some things when we start getting into some stuff where we use those residuals. All right, now what we'll also create, and this is one of the ways we're going to verify that your linear model is a good fit for our data, is we're going to talk about putting together a residual plot. These are still my x values. Okay, but what I'm going to plot on the y-axis this time will be my residuals. Okay, so maybe at x equals 1, I have a residual of 0.2. X equals 1.2, maybe my residual is negative 0.1. Okay, so again, we'll get a plot of all my residuals because we're looking for some things. What I want is no pattern. I'm sorry if you didn't get that. Okay, I want no pattern. Okay, so this is a good situation. My points are scattered out. These are bad. I don't want to see a curve. Okay, because there's a pattern. Another type of situation is as x increases, my residuals are getting larger. That's another pattern that's going on. I don't want that. That's another bad situation. Okay, so I don't want to see a pattern. Now what you got to be careful of is we'll put together a residual plot once in a while. Some people get mixed up and think they're looking for a linear pattern. Okay, we're not looking for a pattern. Okay, we don't want a pattern. So we have to keep track of what am I looking at. Am I looking at the plot of my original data, or am I looking at my residual plot? All right, now a couple definitions we run into. The standard deviation of your residuals. Okay, and we represent it with S. Okay, because when we start getting into some of our inference with our linear regression, we'll get a table and they'll have that value for S. What it means is your average size of prediction errors, or your residuals, when using the regression line. So what it is, okay, if you think about definition standard deviation, the average distance we are from the mean. Okay, this is talking about the average distance we're off. Okay, how far are my residuals off? Okay, so that's what your standard deviation is. Now we really kind of want to understand that definition. Okay, so if we're ever asked to interpret what S means. Another one we're really more concerned about at definitions to coefficient of determination, R squared. Okay, it's defined as a fraction. Okay, or percentage or proportion of variation. Okay, so it's a measure of variation in one variable that is accounted for by your least squares regression line on the other variable. Okay, so again, it's going to be mostly a definition. Okay, now the other thing is, if you remember, I said that when the absolute value of my R correlation was less than 0.7, okay, we want to call this weak. And here's the reason. If R equals 0.7, R squared equals 0.49. That's less than 50% of our variation being explained. Okay, so it's less than 50% of the time where we think that there's a relationship between x's and y's. All right, now we talked about earlier when we have outliers. Okay, we have a couple situations. Okay, I could have an outlier here. Okay, or I could have an outlier here. Now, one of these is just simply going to be called an outlier. Another one's going to be called an influential point. Okay. Now, difference between them. Okay. Outliers don't change your slope in correlation much. Influential points do change your slope and your correlation, okay, by a significant amount. Okay, so what you're going to find out is this is what's going to simply be an outlier, okay, whereas this one's going to be an influential point. Okay, usually what you can think about as your influential point is it's an outlier in the x direction. Okay, even though it may fall on our line, okay, as I extend that out, if it's in the x direction, it will change that correlation and your slope, because really our line would be better fit without it, maybe by going here. Okay, so that's what you can look at. You can always go in, test it on your calculator, type in your data, okay, and look to see how my correlation and my slope change, but that's a lot more work. Okay, so just think about x direction, that's going to be an influential point. Y direction is just simply going to be an outlier. And that wraps up section 2.